안녕하세요. 장병윤입니다. 오늘은 세 번째 주 오퍼레이션 매니지먼트 세미나 2 시간입니다. Hello, graduate student in Operation Management Seminar 2. This is the third week of the lecture. Are you ready to enjoy the lecture? Let's move. Last week, we learned these five topics. First, 가숑 지로트라 네테신 interesting, important, and impactful operation management. I introduced this journal, this article, and then we studied, and I also introduced the Gasong 2012 paper, what is interesting in operation management. But I didn't explain this paper. So today I'm going to explain this paper. But you have homework last week. Don't forget that. And then I talked about what is simulation, advantage of simulation, and simulation history. Before starting today's topic, I'm going to talk about homework. We're supposed to submit your homework at the first time we meet offline. Supposed to April 14th, but because of coronavirus, if we cannot meet offline on that day, April 14th, unfortunately, you should submit on April 14th in BB, Blackboard. You have to submit your homework April 14th on BB. And also for Q&A, I created Q&A sessions week 1, 2, 3 in BB, so you can use that Q&A session, or if you have a question, you can email me. Now let's move to today's topic. First, I'm going to a little bit explain Gasong 2012 paper, what is interesting in operation management, and then I'm going to introduce a new paper. Then we are going to study fundamental simulation concepts. Gasong 2012 paper discuss Gasong's view of essential characteristics of interesting research in general and in operation management in particular. He also talk about what is interesting, meaning interesting means unexpected. Interesting research stimulates your curiosity. It induces a pause for contemplation, and most importantly, it contradicts how you think about the world. In Gasong 2002 paper, he also mentioned confirming what is expected to be true is simply not interesting. Interesting paper would violate our presumption. And also, this paper gives us a formula for interesting. That is, what was shown to be X is really Y. So interesting paper is the careful, because of a careful writing of the author. Interesting papers do not just happen. And then this paper gives us some example, like what was thought to be exogenous is really endogenous. What was thought to be complex is really simple. And what was thought to be simple is really complex. What was expected to be small effect is really large effect. And you can see more example and more formula for interesting. Finally, this paper talk about impact. Interesting research raises more questions than it answers. It is controversial. It invokes responses like they can't be true. What this is obviously incomplete. Interesting research should initially leave the reader a little discontent, unnerved, or motivated to prove it wrong, or at least incomplete. This is why it can be hard to publish interesting research, and really interesting research is rarely accepted immediately. Interesting research that is also important changes behavior. That is, it yields the ever so desirable impact. Interesting times important is equal to impact. Now I'm introducing a new paper. It's Kasong's another paper, 2019 paper. Research framework for business model, what is common among fast fashion, e-tailing, and ride sharing. It is extension of OM research to business model. With this paper, I'm going to give you another homework. You need to summarize this article to 3 to 5 pages, and you should prepare for presentation when we meet offline. This is a good paper. Okay, then it's published in Management Science. It's a good journal. Now let's turn to simulation part. We will learn underlying idea and method and issue in simulation. Now let's consider the simple processing system. We are considering this simple system. Part arrive to the system, then generally it waits here if the server is busy. Then if not busy, then this item coming to the machine, then after service leaves the system. It is a very simple processing system. General intent of the system is to estimate the expected production and estimate the waiting time in queue and queue length and proportion of time machine is busy. In here, you should be very careful about time unit. Time unit can be different unit in different place. Arriving place, serving place, or departing place. But the time unit must declare. We should declare a time unit, and we should be careful to check the unit when specify input into arrival time, and declare a base time unit for internal calculation and output. When we interpret the result, it should be very reasonable. Also, there is a round of error. For the previous system, this is a model spec. In this model, at time 0, empty and idle. For this model, minute is a base time unit. Input data, assume given for now, it's a minute. For part number 1, arrival time is 0 and service time is 2.90, and then inter-arrival time is 173. So 173 minute, part 2 arrival, then service time is 176, and inter-arrival time is 135, and 173 and plus 135, then part 3 arrives 3.08 and then service time is 3.39, something like that. Then we can see, you can imagine the system. Then our simulation start when 20 minutes of time have passed. So stopping time is 20 minutes. Let's see goals of study. Output performance measure. Output performance measure is going to collect some data like total production, average waiting time, or maximum waiting time. Let's see what is that. Total production of part of run. So we have stop our simulation 20 minutes. Then after that time we will see what is the total production of part of run. That is recorded in P, and then we will calculate average waiting time of part in Q. That's another output performance measure. The formula of output performance measure over average waiting time is here. Summation WQI divided by N. Here N is the number of parts completing Q wait, and WQI is a waiting time in Q over iced wait. Then we know that WQ1 is equal to 0. You know why? And N is greater than or equal to 1. Because we have a Q, right? And maximum waiting time of part in Q, we can denote using this notation. Max WQI. I equal 1 to N. Let's see another performance measure. Time average number of part in Q, maximum number of part in Q, average and maximum total time in system of part. First, time average number of parts in Q. It is denoted by this formula. Integrate 0 to 20 QT/dt divided by 20 because we have a 20-minute simulation. QT is the number of parts in Q at time t. And so this formula is a time average number of parts in Q. Then we will collect maximum number of parts in Q. It's denoted by max QT. T is between 0 to 20. Then we will calculate average total time in system of part. It is called cycle time. AKA is also known as cycle time. Then maximum total time in Q. Okay. Then this is average total time in system. TS is a time in system over part I. So summation I equal P. P is what? What is P? P is a number of part. No. P is a total production. Alright? 1 to total production. So TS is for all item you wanna calculate the time in system and divided P is P. Then P then this notation This notation is average total time in system of part, and this is a maximum total time in system. Okay. So, in operation management, do you remember I equal RT? RT. Here T is what? Cycle time. And R is P. R is P. R is P. And I is number of parts in Q. Then we will also consider one more output performance measure. Utilization of machine. It is what? If BT is 1, if machine is busy at time t, 0 if machine is idle at time t, then integration 0 to 20 BT dt divided by 20 is utilization of a machine. Also, many other options are many other output performance measures is possible, but we generally focus on previous measure in our simple processing system. Let's see analysis option. First, educated guessing. We know average inter-arrival time is 4.08 minutes. Average service time is 3.46. So average inter-arrival time is great, right? So on average, parts are being processed faster than arrival. Processed faster than they arrive. We know this fact from here, from these two. So system has a chance of operating in a stable way in long run. That is, might not explode. It's a general kind of a system, like when you go to the restaurant or your manufacturing system. If all inter-arrival and service times are exactly at their mean, there would never be a queue. If this is constant, then there is no queue. But data clearly exhibit variability. They have some distribution, but they have variability. So queue could form. There will be queue. If we have average inter-arrival less than average service time, inter-arrival less than service time, and this persisted, then queue would explode. System explode. In this case, truth, like general system, between these extreme. This extreme is explode or no queue. This is our guessing. Okay, we cannot get more information. Next analysis option is a queuing theory. But queuing theory requires additional assumption about model. What assumption? Can you guess? Our system can be modeled as a MN1 queue, but it needs assumption. This assumption, inter-arrival times follows exponential distribution. This means M means Markovian. Okay, Markovian exponential distribution. Service time exponential 2. Inter-arrival exponential, service time exponential, and independent of inner arrivals. These are additional assumptions. Then we can use a queuing theory, MN1Q formula. And also expected service time and expected inter-arrival time, expected service time less than expected inter-arrival time. and steady state long run forever. So if we have this condition, then what? We have a steady state result. Then we have a MM1 queuing result, exact analytical result. For example, this one is a average waiting time in queue. We get the exact result. I will show you MM1 queue system or later. Then mu A is a expectation of inter-arrival time. Mu S is a expectation of service time. But if we use queuing theory, we have some problem, validity problem, because we don't know our inter-arrival follows exponential distribution, our service time follows exponential distribution. Okay, and time frame problem and estimating mean. You should estimate mean. And this assumption open useful as our first cut approximation, but we don't know. And here, estimating mean means what? Steady state mean. What we do not estimate the mean as steady state. It is a terminating system. I will explain more terminating system later. Now, another option is a mechanistic simulation. Individual operation arrival service time will occur exactly as in reality. We check every details, arrival and service time, and check movement, change occurs at right time, in right order, and different pieces interact, install, observe to get upper performance measure. Then we use a concrete analysis approach, brute force analysis approach. Nothing mysterious or subtle, but we need a lot of detail and bookkeeping. Simulation software keep track of things for you. Okay, if we use simulation software, then even though it's detail or bookkeeping, simulation software works for you. For simulation, you need to know some concept for simulation. That's a piece of simulation model. The first one is entity. Entities are players that move around, change status, affect and are affected by other entity. It is players. Dynamic object, entities are dynamic object, get created, move around, live. Because it is created, move around, live, that's why it is a dynamic object. Usually represent real things. In our model, entity are parts, and can have fake entity for modeling trick. Usually, entity have a multiple realization floating around. Entity, it can have a different type of entity concurrently, and usually identifying type of entity is the first thing to do in building model. Okay, in to model a simulation or for simulation model, usually first thing to do is to identify types of entity. Another concept is attribute. Attribute is a characteristic of all entity. Attribute describe, differentiate all entity because it is a characteristic of all entity. All entity have the same attribute slot but different value for different entity. This is example of attribute. Time of arrival, due date, priority, color is it's example of attribute. Attribute value tied to specific entity. So it is like a local variable to entity. In Arena, some of attributes are automatic, but some attribute you can define yourself. Now variable. Variable reflect characteristic of whole model, not of a specific entity. A variable used for many different kind of things. Travel time between all station fare, number of parts in system, simulation, clock. It's a kind of variable. Name variable which there is only one copy for whole model, not tied to entity. Entity can access, change variable. Variable it is kind of writing on wall. It's rewritable. Some built in by Arena. You can define others. Now let's talk about resource. Resource is what entities compete for. People, equipment, space is an example of a resource. Entity sees a resource and use it, release it. Think of a resource being assigned to an entity rather than an entity belong to a resource. A resource can have several units of capacity. Seats at a table in restaurant, seats have a lot of several units of capacity, and identical ticketing agent and an airline counter. You can think several agent. So it has several units of capacity. Number of units of resource can be changed during simulation. Queue. Queue is a place for entity to wait when they can't move on. Maybe since resource they want to seize is not available. In that case, entity wait in queue. Queues have names often tied to corresponding resource. Queue is corresponding to resource often. A queue can have a finite capacity to model limited space and have to model what to do. If an entity shows up to a queue that's already full, we usually watch length of queue, waiting time in queue. Let's see, statistical accumulate. It's variable that watch what is happening. Statistical accumulate depend on output performance measure desired. Passive in model, don't participate, just watch accumulate. Many are automatic in Arena, but some you may have to set up and maintain during simulation. At the end of simulation, used to compute final output performance measures. And these are statistical accumulate for simple processing system. A previous example, number of parts produced so far, statistical accumulator, total waiting time spent in queue so far, number of parts that have gone through queue, maximum time in queue we have seen so far, total of time spent in system, max time in system if been seen so far, area so far under the queue length curve QT, max of QT so far, area so far under sub busy curve BT. These are statistical accumulate. With this one, we are going to analyze this simple processing system. Okay, simple processing system. And now I think you are ready to start simulation. Okay, so I'm going to give you simulation software web page, and then download the trial version and install your simulation software and try a simple simulation part. Okay, I think you are ready to play with the arena. This is a website of arena. So go this and then download the trial version and play with it. I'm going to upload some example, then you easily can play. Okay, let's finish today's lecture. Today I introduce this paper, explain this paper, and you have homework for this paper. It's extension of OM Part 2 business model. Then I am talking about some part of idea method of issue in simulation with the simple processing system. So I think you are ready to simulate now. You play with the simulation, okay, and see you next time. Bye.